In this video, we're going to be looking at topic 1B, elements, compounds and mixtures, and this is part of the IGCSE chemistry course from Edexcel. Now, the outcomes in this topic are seen in single, double and triple, so they are completely the same across each of the three levels. So we're going to be looking at how we classify substances. We'll be looking at how we can identify a pure substance in comparison to a mixture. We'll be looking at separation techniques, specifically distillation, filtration, chromatography and crystallization. Going into a little bit more detail about chromatography and how to calculate RF values in chromatography as well. So we're going to start off by looking at some of the key terms that we have to know in terms of the different types of substances that we need. Now, this is something that you should have covered in Key Stage 3, so it should just be a bit of revision, but we'll go through it to make sure that you have the definitions complete. So we're going to start off with elements. We can define elements as substances that cannot be split into anything simpler by chemical means. And this is probably a little bit different to what you learned in Key Stage 3. In Key Stage 3, you most likely learned that elements contain only one type of atom. Now, unfortunately, we cannot use this definition anymore at Key Stage 4 because elements can contain slightly different atoms, and this is something that will be covered in topic 1C. What we do know, however, is that a pure metal like magnesium is only going to be made up of magnesium atoms, and it can't be split down into anything further. Oxygen gas is going to be made up of O2 molecules, so two oxygen atoms stuck together, and diamond is only going to be formed of carbon atoms. So elements are made all from the same type of atom, but there can be slight differences to them. So we're going to just keep it as they cannot be split down anymore. Compounds, however, are formed when we get two or more elements that are chemically combined or chemically joined. And compounds are going to combine in fixed proportions. And you will learn that that is then linked to their chemical formula. And you'll learn how to write chemical formula later on in this course. So for example, if we have water, every single water molecule, or every compound of water that is made from two hydrogens with one oxygen. So water is H2O. Now silicon dioxide is going to form SiO2. So for every one silicon, there are two oxygens, and that's something that we'll talk about later in covalent bonding. And for sodium chloride, it is NaCl, meaning the compound is going to have one sodium for every one chlorine. And again, that's something that we'll talk about later when we do ionic bonding. But the compounds are when we have these elements chemically joined. Mixtures, however, are slightly different. This is where we have various substances mixed together and we have no chemical reaction. So these are not chemically joined together. They simply occupy the same space. And mixtures can be made up of elements, compounds, or a combination of both. So for example, here we have a mixture of nitrogen and oxygen, but notice that the nitrogen and oxygen are not joined together. They just simply occupy this box. We have got here carbon dioxide and H2O, or water vapor. Again, not joined together. The compounds themselves are joined, but they are not then joined to each other. And then we could have CO2 and nitrogen. So this is an element and a compound in the same space, giving us a mixture. So mixtures are slightly different, that they are then made up of elements and compounds or a combination of both. Now in a mixture, each element keeps its own properties. Okay, so if we have a mixture of carbon dioxide and nitrogen, the carbon dioxide and nitrogen have specific properties that you then see in this mixture. This is different, however, for a compound, as in a compound, the properties change. For example, if we look at water, we know that water is H2O, made of hydrogen and oxygen. So a mixture of hydrogen and oxygen is a colourless gas. Okay, so if we have H2 and O2 mixing together, it's a colourless gas. If we put a flame near that, it will explode. Very flammable. However, water, made up of hydrogen and oxygen, but this time bonded or chemically joined together, it is this time a colourless liquid. And if you put a flame near it, it will put out the flame, because we know that water can be used to douse a fire. So when we have the mixture, we keep the properties. When we make a compound from those elements, they change and form new properties depending on the compound that you have formed. Another key difference between mixtures and compounds is the ease of separation. So mixtures can be separated by physical means, meaning we can change the temperature, we can dissolve part in a solvent, we can do something like chromatography, which we'll talk about later, we can take advantage of magnets. All of these methods are going to be easily separating mixtures. Compounds are not easily separated. And triple students will learn about electrolysis as a method of separating compounds. If, however, we have a mixture, for example, iron and sulfur, iron is magnetic because it's a metal and the sulfur is not, so this mixture can be easily separated using a magnet. And your teacher might actually do this experiment with you so that you can see that separation. But once we combine the iron and the sulfur and chemically join them to make iron sulfide, we can't separate that anymore. If we try to separate it, it's going to require huge amounts of energy. So the rest of this topic is now going to focus on how we separate out these mixtures. As I've said, compounds are a lot more difficult to separate, so we don't go into a lot of detail about them. We're only going to focus on how we separate mixtures. So there are 4 key methods that we can use. There's filtration, crystallization, distillation, and paper chromatography. Now you've probably seen some of these back in Key Stage 3, most likely filtration and probably paper chromatography. What we're going to do is just go into more detail about them. You are expected to be able to explain each of these methods. So we need an explanation. And you should also be able to draw a diagram of each of them as well. So we're going to go through each of these just now. So let's start off with filtration. Filtration can be used to separate an insoluble solid from a liquid. For example, sand from water. This is the most common filtration that you would do in the lab, and is one of the easiest. And again, your teacher may do this experiment with you. So in your diagram, you've got your funnel, or sometimes known as your filter funnel. You have filter paper inside that is there to catch the sand, and you then pour your mixture of your water and your sand through the filter, and what happens is the water passes through and is known as the filtrate, and the sand is kept in the filter paper, and that is known as the residue. So our residue is what's left in the filter paper, whether it's sand or any other insoluble solid, and the liquid that passes through is known as the filtrate. So make sure that you can draw that out, of course making sure that you use a ruler for any of your chemical drawings as well. The next method that we're going to look at is crystallization. So crystallization this time is used to separate a soluble solid from a solvent. And the most common example is sodium chloride or table salt from water. Again, this is a very common experiment that you may do with your teacher. You have this set up as shown in the diagram. So you have a tripod stand with some sort of heat source, and that's usually a Bunsen burner. You have a dish with your sodium chloride in it, and that is placed on top of some gauze or some wire just to make sure it doesn't fall through the tripod. And then what happens is we heat the solution in order to remove some of the water, probably about 3/4 of the water, and we then allow it to cool to room temperature. That then allows the crystals to form, and we then remove the crystals by filtration. So crystallization doesn't get rid of all the water when we heat it. We want to keep a small amount of the water, and we want to form a saturated solution which we learned about back in topic 1A. And in order to test that, we put a glass rod into the mixture. And if we start to see crystals being formed, we remove the heat source so that we are left with a small amount of solvent and our crystals that are starting to be formed. And we then leave it to cool somewhere warm, usually in the lab near a window, and then that'll allow the rest of the solvent to evaporate slowly and allow your crystals to form. And if you do have any solvent left over, they are removed during the filtration process. So another method of separation is simple distillation, and this again can be used to separate out the components of a solution, like sodium chloride. The difference this time is we want the solvent. So when we do crystallization, that's when we want the solute, or we want those crystals. When we do distillation, it's the water or the liquid that we want. That's the difference between the two methods, because they both separate the same thing. It just depends on what your desired end product is. So the way that we set up simple distillation is we have this round bottom flask filled with our sodium chloride solution, and it would be placed on, again, some sort of gauze or holder that has a heat source, or typically a Bunsen burner. And then as you start to heat the liquid, it will eventually start to boil and form a gas. The gas particles then travel up and they go down the side arm of the flask and then into the condenser. And the purpose of the condenser is to turn the gas into a liquid. So it's going to have all the vapour from our solution being cooled down, turning into a liquid, and then it goes into our beaker. So typically we would heat this up to boil, so to 100 degrees, boil the water and to form water vapour, it passes through the condenser, and then we get the pure water. And we'll be left with our sodium chloride salt in the round bottom flask. But of course that's not easy to get out, which is why we don't use this method if we want the salt crystals. In this case, we want the pure water. Now, the last method that we need to know is called paper chromatography. And again, this is probably something that you've done at Key Stage 3, and most likely you will do this in your lessons with your teacher as well. So paper chromatography can be used to separate a variety of different mixtures, but the most common mixtures are inks and dyes, because they have colours and we're easy to see the separation. So what happens is when we put our substance into this separation method is we can see the colours being separated, and it's because we have a solvent and some coloured substances will dissolve better than others. So how does this actually work? Well, we have this set up here. We've got the beaker and we have our chromatography paper. And this is a special type of paper that allows the solvent to travel up it. And we put a pencil line approximately 1 centimetre from the bottom. And it's very important that it is a pencil line. If you use a pen or any other felt tip or marker, it's going to interfere with your results because we're analysing an ink or a dye. We don't want to be adding any more ink. So we have to use a pencil. And what we do is we put a spot of our ink or dye on the pencil line. We then put the chromatography paper into the beaker, and it's usually on top of a watch glass or on top of a splint to hold it in place, and we don't want it touching the bottom. Okay, we have it sitting just above the bottom, and then we add in our solvent. Now the solvent typically is water, but it can also be an alcohol. It just depends on what dye or ink it is that you're using. And again, it's very important, if you notice here, that the solvent line is below the pencil line. And the reason that we do that is if we have the solvent above the pencil line, the ink will travel down into the solvent, and we want it to travel up the paper. Once we have our solvent and we have our chromatography paper, what happens is the solvent starts to travel up the paper like that. And we can see that this point here, the solvent front is how far up the paper the solvent has travelled. And as it travels up, it starts to separate out the ink. And in this case, we get 3 different types of ink: spot A, spot B, and spot C. And how far they travel is all dependent on how much they are attracted to the solvent. Now, we don't need to go into much detail about that. All you need to know is that the more soluble the substance is, the further it travels up the paper. Okay, so the more it can dissolve into the solvent, the further up the paper it is going to travel. But our main focus is the fact that it then splits. Once the solvent gets up to a certain height, probably about 3/4 of the way, you don't need to go all the way to the top of the paper. You take it out of the solvent and then you leave the chromatography paper to dry before you move on to the next stage. Once the chromatography paper is dry, you will get something known as the chromatogram. And a chromatogram could look something like this. So you can see that we have got, in this case, our standards. So we have a red ink, a blue ink, and a yellow ink. And then we had a mixture where we didn't know which ink was containing. And then we've now got 3 dots. And what we can do is we can then check the distances of each spot in order to identify them. Now, in this case, it's quite easy to identify because, of course, we can just look at the colour. But sometimes you may get ink where the colour is quite similar, so you can't really tell them apart. And that's where we have to use this value known as the RF value, or the retardation factor, in order to determine this. And it is useful when the spots have the same colours but they have different distances. So if, for example, we had 2 blue spots on this chromatogram, we could then figure out which one is our actual blue ink by using the RF value as opposed to just looking straight at it. So we work out the RF value by measuring 2 things. We measure how far the component moved, which is how far the spot moved, and then the distance travelled by the liquid. And we do the distance by the component divided by the distance of the liquid. And an RF value has to be between 0 and 1. If you get an answer that is above 1, you have done something wrong. And the most common mistake is to get these the wrong way around. That would give you an answer above 1, but that would be wrong. You want to make sure that the spot goes on top and the solvent front goes on the bottom, i.e. the smaller number on top, the larger number on the bottom, because your spot is not going to move further than your solvent front. What you would then do is you would measure it, find out the value, and you could then compare that to a standard reference. You'll be able to find databases of RF values that will have all of these numbers in it, and you would compare that to the standard. Now, it doesn't matter how far you let the solvent front go, this is a ratio. So it would always give you the same number regardless of the distance that you allowed the solvent to move. Okay, if you are repeating it to compare the same values, of course you have to make sure that you keep it as fair as possible, so you use the same type of paper and the same solvent, because they can have a small effect on the RF values that are calculated. Let's look at an example of how to calculate the RF value. We have a chromatogram here, and you can see this time we can't use colours because our spots are all black and white, but what we want to calculate is the RF value for substance D. So we're going to need to measure 2 things. We're going to need to measure the distance that the solvent travelled and then the distance that spot D travelled. So we're going to start at the baseline, and the baseline is another phrase for the pencil line, and we're going to have to measure up to the solvent front, in this case known as the final water level. All of these terms are interchangeable, so it doesn't matter which one you use, just be aware what each of them mean. So we measure this distance from the baseline to the solvent front, and our solvent has moved 68 millimetres. Now you could measure it in centimetres if you wish, it really doesn't matter, you are going to get the same value. We then measure the distance that spot D has moved, going to the centre of the spot, and spot D has moved 55 millimetres. So then to work out the RF value, I do the distance of D divided by the solvent, which gives me 55 over 68, and gives me an answer of 0.81. No units required, and our number is less than 1, so it's highly likely that this would give us a correct answer. You are expected to be able to do RF values in your exam, so it is important that you do make sure that you have a ruler in your exam, because this is a very common exam question. You are allowed a slight degree of error where they give you some leeway or they ask for a specific range, but it's usually only a millimetre or two. So you have to be very careful and make sure that you're measuring as closely as possible. So let's finish up with some past paper questions on this topic. The first one is to look at the contents of each box, and we want to classify each as a compound, an element, or a mixture. So with the first one, we've got some gold, we've got some sodium cyanide, some oxygen, and some water. And notice that none of these are connected, so this must be a mixture. We then go to the second box, and we have that sodium cyanide, so we have Na, C, and N. That can be broken down into those different elements, so it can't be an element. They are all the same and they're all joined together, so this has to be a compound. And then in the last box, we've got 2 atoms of gold and 2 molecules of water. Again, they're not joined, so this is another example of a mixture. Now, don't be caught out by the fact that we haven't used element. It doesn't say that all 3 of them will be used. They give you 3 options, but just be aware that 2 of them may be the same. So don't go changing your answer if you're not sure because you haven't used element. Stick with your gut. So the student here uses a dropping pipette to place a drop of green solution onto a chromatography paper, and he gets this chromatogram. And we can see the diagram here. So we want to add 3 labels. We want to be identifying the solvent, the chromatography paper, and the original spot of the green solution. So the solvent is going to be this one here. It's obviously the water or the liquid at the bottom. The chromatography paper is the rectangle, and then the original position of the spot should be right there, because the spot would be on the baseline and it should be in line with the others as well. Okay, so it has to be below the visible spot, so you can't put your spot over here because that wouldn't give you that chromatogram, so that would be wrong. And then explain how many different dyes are present. Well, we have 4 spots, so we must have 4 dyes. And because we have to say explain, we must say why. So there are 4 dyes because there are 4 spots. And there you can see the mark scheme for those questions as well. One more question, just to look a little bit more at the separation techniques. We want to place a tick in one box to show the best method of separation for each mixture. So we have P, Q, R, and S. And we can be looking at chromatography, simple distillation, filtration, or fractional distillation. Now, we haven't talked much about fractional distillation. You will look at this more in organic chemistry. This is when we have substances separating. So we're going to separate using boiling points. Okay, so it can come up, of course, in the exam paper, because by the time you do the exam, you will have done all of the different methods. But here we haven't talked too much about it, but we'll see if we come across one. So first of all, we want to look for red ink from a mixture of coloured ink. Well, we know that the best way to separate out inks is chromatography. The second one, we want to get some ethanol from a mixture of ethanol and water. So this is separating out 2 liquids. So we're going to separate them using their boiling points. So this is fractional distillation. Simple distillation tends to be if we have a solid and a liquid, whereas fractional distillation would be multiple liquids. So R, a mixture of sand and water, and we want the sand. So that would be filtration, because it would be caught into the filter paper. And then lastly, the water from a copper sulfate solution. So we don't have crystallization as an option, so it must then be our simple distillation, because we want the water from a solution that contains a solid. And then which of the mixtures P, Q, R and S will contain an undissolved solid? Well, that's what one essentially is insoluble, and that must be R, because the sand is insoluble from the sand and water. Impure dry crystals of magnesium nitrate can be obtained by crystallization, and we want to look at the different steps of how to do this. And they've given us the steps, but they're in the wrong order. And we want to then put them in the correct order for 2 marks. So we have allow the solution to cool to room temperature, heat the solution to evaporate some of the water, pour the mixture of crystals and solution through filter paper, put the crystals in a warm place to dry, and dip a glass rod into the solution to see if crystals form. Now, we've been told that E is the second step. So the first step is going to have to be us getting rid of some of the water. So that's going to be B, where we heat the solution to evaporate some of the water. So we've used B and E. The next step then would be, once we've removed some of the water, we've got our crystals forming on the glass rod, we remove it from the heat and we allow it to cool to room temperature. So our next step is A. That then leaves us with either pouring the crystals in the solution through filter paper or leaving the crystals to dry. Well, we have to actually separate them first, so our next step must be C, to pour them through the filter paper, and then the last step is D, to allow them to dry. 2 marks for that question. And there we can see the mark scheme for those. Now that's everything for topic 1B, elements, compounds and mixtures. If you do have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.